Hi, so today we are here to do this experiment on Newton's ring. So before we begin, just a couple of things what this Newton's ring is all about. So what happens, I'll show you the diagram, not to worry, I will show you the diagram. But if you have a plano-convex lens, what is plano-convex lens? This is a convex lens. So plano-convex is the one which has one side flat, plane, and one side in a convex shape. Fine. So a plano-convex lens, which it's a convex surface placed on the glass plate. So if you have a glass plate on which if you place this plano-convex lens, okay. So if you see the thickness is quite not same, correct? This is a very thick one and it keeps decreasing as you go right at the center. Okay, and of course it is zero at this point. So there is a gradient. You can see the thickness of the air, over here between the lens and the glass plate that is clapped here. Okay, I will show you the diagram, don't worry, but just a brief thing. There's a variation in the air over here, okay, and when a light enters into this area, okay, an interference takes place. Now this interference that takes place will be undoubtedly out of phase, okay, it will be out of phase for sure, because of this variation in the thickness between the air. And this out of phase phenomena, which will then reflect and go back into the microscope which is watching here, or your eyes which is watching this through the microscope, is going to see this change in phase kind of a pattern, on which will actually form fringes, okay, dark and bright bands, but only difference because of the shape of the lens, it will be in the form of rings. Okay, it will be forming in the form of rings. Okay, so very interesting thing. And using these rings, okay, you'll find this interesting. Using these rings we can actually find the radius of curvature of the lens that we are using. Okay, so we are actually going to do that in this experiment. All right, condition is that you need to have a monochromatic light if you want to do your experiment properly. If you use a white light, obviously you'll see a rainbow of rings, okay, different colored rings you'll see. But if you want to do little carefully your readings, you need to use a monochromatic light so that the rings formed are of single color. Okay, so this is named after Newton because it was Isaac Newton who had discovered this phenomena. So it's named as Newton's ring. Fine. So let's not waste much time. Go to the experiment. The aim is to determine the radius of curvature of the convex surface of a lens by the means of Newton's ring. Apparatus that you would need is a glass plate, a plano-convex lens, a monochromatic source of light. We are using a sodium light. Okay, we are using a sodium light, a magnifying lens, and a traveling microscope. Fine. This is the formula that you need to remember. The D is the diameter separation between every ring. The diameter of every ring is the dn. The n is for the number of ring, okay, and it is squared. For n is again the number of ring and the wavelength lambda. You can also use find the radius of curvature using the graphical method, that is a slope upon 4 pi, where slope you will get by plotting a graph of number of rings n versus d square. Okay, so d square upon n would give you slopes of 4 lambda. So here the same thing what I've told is listed in green here. So next, this is the apparatus. You will need a traveling microscope. Okay, you will need a traveling microscope, and traveling microscope has 3 scales. It has a scale over here, it has a scale at this point, and it has a scale down here. So the one which I'm showing you now is meant for upward and downward movement. Okay, so we do not use it in a Newton's ring experiment, the upward and downward motion. The motion that we will use is sideways for Newton's ring experiment. Fine. You can even use this platform, but not much you'll be able to move. So you better use this one. All right, use this platform to move sideways. Okay. So I've tried to zoom it. The least count of whichever, there are 3 scales here. You can use any one of them. The least count of that will be equal to 0.001. Okay, because the smallest division is 0.05 divided by the number of divisions 50. Okay, so if you do that, you'll get 0.001. So least count of any scale that you use here or here or here, it will all be 0.001. Fine. You have a scale here also. Okay, this is a bit clear. You can possibly see that there are 50, number of divisions are 50. Okay, and the smallest division is not yet still clear on this. Okay, cannot click that clear picture on a steel scale. And then of course this one. There are these things to rotate up and down. Okay, and these is for finer adjustments of the microscope. This is for moving of the microscope up and down, and this one for moving it front back. And okay, front back, and obviously there's one here, which you can use to move it sideways. All right, so there are 3 knobs in total for all the motions up and down and so on. Okay, and for finer adjustments you can then use this one, all right, to get a clear picture of the Newton ring. So this is the experimental setup. You can see the experimental setup, a very simple experimental setup. This is the sodium source here, sodium source of light. There is a, so before let me just go one by one. This is the glass plate on which the lens is kept. You can see the lens which is kept down here. Okay, and this is the glass plate, and you can see it is movable. Okay, and mostly we always set it to almost 45 degrees. Okay, the angle at which it is kept is almost 45 degrees every time. And of course the ray of light would enter through here. A part of it would go down and a part of it will come up, okay, to brighten up. There's a magnifying lens. I hope you can see a magnifying lens whose focal length is around 24 centimeter. How did we find that? We found that you might have done this kind of method many a times in your higher secondary. Okay, you take a magnifying lens and use a long ruler and find the reading till you get a clear image of the distant object. You can see we can see our college building here and the trees and all in the magnifying lens. Okay, so you do this, and this is the college building. Okay, and these are the trees around. Inverted images you will get. So you move this till you get a very clear image, and you measure it, and it's around 24 centimeter. Fine. And if your setup is all fine, then you will find Newton's ring. These are Newton's ring. Okay, we will see that during the experiment. Okay, so these are the Newton's ring, and you can see alternate dark and bright bands in this circle. We will focus more on the bright bands. Okay, and the way we will measure it is from almost a 6th ring up to 15th ring. Okay, I will tell you. So we will have we need to first of all focus it such a way that we get 15 rings on the left hand side and almost 15 rings on the right hand side. Okay, from the center. All right, and we will take the reading from 15 up to 6 and then move on this side from 6 to 15. Now why do we ignore this? You can see, I don't know whether its image is very clear. You can see these are not that concentric. Okay, you can see these rings are not so concentric. So we move down to almost the next lower down, where rings become almost very circular. Okay, so 6th onwards. So instead of going zigzag like this and like this, what we do is we place the microscope right at 15 to start with, and then we move right from left side to the right side. Right from left side to the right side we will go measuring the rings. Okay, measuring the position of the ring using the traveling microscope. So here is the ray diagram that we have. Okay, here's the ray diagram that we have. Here's a sodium source. You must have seen the sodium source in the previous slide. This is the sodium source, the light from which it comes out. Okay, so yellow, bright yellow, right? And so this is a sodium source, and then we have the condensing lens. That was a magnifying lens which was kept at 24 centimeter. Correct. Okay, and then it would go parallelly, hit on this glass plate which was kept at approximately 45 degrees, go down, giving a reflecting glass plate. There's already one more reflecting glass plate down so that the light can come out nicely. More than that, it can give us brightness. Okay, and then we would get a pattern which will look like this. Fine. All right, so next, so what we'll do is now we will go to the laboratory, perform this experiment, and let's see whether Newton rings actually work. Okay, get our data and try to calculate the radius of curvature. Fine. All right, so see you after the experiment with the data. Alright, so I have done the setting. You can see I have adjusted for the parallel light here initially, and you can see they cannot see any rings as such, but you can see a bright yellow light of sodium source coming inside. Okay, at least this much of bright yellow light is required. And next what we are going to do is we are going to place this plano convex lens under it. Okay, what do you mean by plano convex is that on one side, one of the side is flat plane and other side is convex. Okay, so when we place the lens on the convex side, okay, when we take the convex side and place it on the glass slab, okay, so you will find rings. Okay, we will see the rings. Since Newton had found it, it is named as Newton's ring. Okay, so we will see this Newton's ring now when we place the convex side. I don't think I'll be able to show you in the camera. Okay, anytime you come to the physics laboratory in our college, you can always see this. It has one flat side and one curved side, and we are going to place it on the curved side under this. Okay, always there is already a glass plate here which is going to reflect the light coming from the source through the microscope, traveling microscope. This is the reason you are seeing a bright light, because there is already a glass plate here to reflect that light. Okay, so we have this now glass plate which I'll place here, adjust and show you the Newton's ring. So let me adjust it now. Alright, so now I have set this Newton's ring for you. As you can see, this bright rings that has formed. I've placed the magnifying lens here, and you can see in the left side of the video, you can see the rings that are formed. And this is the traveling microscope scales from where we will be taking the readings. So let me just adjust it a bit more for you so that you can see it a little clear. Okay, fine. You may not be able to read the readings, but I can hold a magnifying glass for you to show what the reading is later on as I'm taking the readings. Fine. So this is how the rings are. So initial setup, what we will do is that we have to take readings for 15, 14, 13, 12, 11, 10, 9, 8, 7, 6 rings. And similarly, we need to go on the other side of the ring to take readings for 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 rings and so on. All right. So what we could do is place ourselves initially at the 15th ring to start with. Okay, and then move on in one of the directions till we go to the 6th ring, and then go down to the central ring, move on up to the 6th ring, and then go to the 15th ring. Is that fine? Okay, so that's the way we will carry on this experiment. Okay, so what we could do to start with is just check moving the traveling microscope. Now as I'm moving the traveling microscope, the rings might get a little distorted because the instead of eyes we are looking at the rings through the camera. All right, now because of that there could be little distortions as I'm moving it, but I will try my best to keep the camera as focused as possible as we are moving across the ring. Okay, so before we start the experiment, let's see whether we can move the traveling microscope from 16th ring to 15th ring to the 15th ring or no. Okay, so let's do that first. So first I'll just move it. So this is the first ring, second ring, third, fourth, fifth, sixth, seventh, eighth, ninth, 10, 11, 12, 13, 14, 15, 16. Yeah, it goes up to 16 on one side. Let us see whether it goes up to 16 on the other side or not. So this is the central ring. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me just go roughly 11, 12, 13, 14, 15, 16. Fine, it goes up to 16 ring on both the side. So let me come down to the center now. So we have two sides, either the left hand side or the right hand side. Okay, and we need to take the MSR and the VSR reading from the scale here. Okay, so let's go to the left hand side, the 15th ring, and then carry forward to the right hand side, 15th ring. Okay, fine. So remember the in between the readings of the ring, that is 1 to 6 we are ignoring. We are taking the readings right from the 15th bright ring to the 15th bright ring on the other side. All right. So right from the center, let me move. So this is my first ring, this is the second ring, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13, 14, 15. Fine. So it's a bit distorted now, but I don't know whether I can touch the camera for you to make it a little brighter. Yeah. So I've reached the 15th ring. I've reached the 15th ring. So let me take the first reading. I hope I can show you using the magnifying glass what the reading is. Microscope. But before that, let me adjust here. It is 8.15. I don't know whether you can see it. It is 8.15. Just have a look. 8.15. All right, it's 8.15 on the. I've just put a magnifying glass in front of the lens. It's 8.15, the main scale reading. And let me see the vernier scale reading. So it is vernier scale reading is 7, 8. Okay, vernier scale reading I'm getting as 8. So let me note it down. Vernier scale reading is 8. Let me move to the next bright fringe slowly. So this is the 14th bright fringe I am on. Let me note down the reading for the 14th bright fringe. It is still 8.15, but it is lesser than 1.5. So let me note it down as 8.1. And the vernier coinciding reading is 8.1. So let me just note down before I forget, 8.10. And vernier reading is 14. So let me just note down. Vernier reading is 14. All right, let me just cross check once again whether it's 14. Yes. Let me just move to the next fringe. Be very careful. So we are on the 13th fringe, 13th ring I mean, and we having 8.1 again, 8.10. I don't know whether you can see it very clearly on your screen. It's 8.1 still. And let me see the vernier reading. 12. I've got 12 vernier reading. So this is the 13th one. So let me just note it down as 12. Let me go to the next ring. Very carefully, very bright one, next one. All right, so that's the next one reading. So let me now note it down as 8.1 again. All right, 8.10. And vernier reading is what I've got is 9. All right, so I don't know whether you can see the vernier reading clearly, but I will just show you using the magnifying glass. Okay, at least 8.1 is quite clearly seen. Okay, but not the vernier reading. Fine. Okay, sorry about that. Let me go to the next ring I mean. There we are. So let's take the reading again, and it is still on 8.1. So I'll note it down as 8.10. I'm just noting down whatever we are getting, and we'll see what is the vernier reading. Vernier reading is so I got 10 this time. Don't know, should have, but let me just write down whatever I got. It is come as 10. Let me go down to the next ring. Okay, so I'm going down to the 10th ring now. I'm on the 10th ring, and we are supposed to go this way up to ring number 6. All right, so the reading here is again, it's still at 8.1. So let me just write it down, 8.1. And the vernier reading is 7. I can take it as 7. I've got a 7. So I got this. Let me go down to the 9th ring number 9. All right, so this is ring number 9. It's come little slightly less than 8.1, but not good enough to write 0. So I'll just note it out as 8.1 still. And let's see what is the vernier reading. Vernier reading this time is 48. Let me note it down as 48. It's much higher than what I was getting for the others. Anyways, let me just note it down. Let's go to the next ring. There it is. We are on the ring number 8, and this is now much below 8.1, almost close to 8.05. So let me write it as 8.05. And the vernier coinciding reading is 43. It's 43. Let me just note it down. 43. Let me go down to the next ring. All right, this is ring number 7, and I need a magnifying glass to look at it. It's 8.05. 8.05, and vernier readings are 35. I'm just noting down whatever I'm getting, as you all can also see. So next, moving down to the next ring. This will be the ring number 6, and we will then move to the next side. Again, 8.05. 8.05, and vernier reading, coinciding vernier reading is 31. I just noted down 31. Fine. So this way we have done with the left hand side reading. So okay, we'll now go to ring number 6 of the right hand side and move on up to ring number 15, taking the readings. Okay, fine. So we are not going zigzag left right, so we are going in one direction. Okay, we are going in one direction, following up to ring number 15 to ring number 15, left to right. Okay, so that there is no error that is added up in the traveling microscope. But let's see what we get, the final reading. We don't know with all these additions that we have done with cameras and all, it's quite uncomfortable. And also we are looking at the ring through the camera. Okay, so that also will add to some error. We will see. Okay, we will see. So what we will do is we'll just go ahead and go to ring number 6 on the other side. So this is first bright ring, second bright ring, third bright ring, fourth, fifth, sixth. Okay, so let me just go back again. First, second, third, fourth, fifth, sixth. Fine. So we are on ring number 6. Okay, we are on ring number 6. Let me just adjust the crossfire. Okay, we are on ring number 6. Let me take the reading for ring number 6, and it is 7.6, 7.7, 7.8, 7.6, 7.7, 7.5, 7.75. So I will take the reading as 7.75. Actually, let me just look at it once again. It could be even 7.78. Let me just guess it. I think I should take it as 7.78 instead, because it's very close to it, but of course little below it. Okay, so 7.76, 7.77, 7.78. I think I can show you on the magnifying glass also. All right, so see here, and try to look at it as much as you can. Fine. And then let me take the vernier reading, I mean the coinciding reading that I am getting. So the coinciding readings are, so I'm getting 13. Let me note down. Okay, let me note down. So 13. Let me go to the next ring. All right, so note down the readings. So this is 7.67. Let me still continue with say 7.8, and vernier reading is 4. Let me note it down as 4. Vernier reading is 4. Go to the next bright ring. All right, so again this will be 7.67, 7 point. Now I think it is a good time to change from 7.8 to 7.775, because it has come quite down now, almost close to 7.5. Okay, so now let me take the vernier reading, and it is it's going to be 4, 5, 6. All right, I can see the 13th. Okay, the 14th one coinciding. So let me just note it down. 14th one. Let me still go to the next ring. All right, so this is the next ring that I got. So let me again check the reading. 7.75. Okay, 7.75. And we look at the vernier reading. 6.7. So 7 is the reading that I got. Okay, fine. So let me now move to the next one. Let me move to the next ring. Okay, so in the next ring, we again look at it. 7.75. All right, 7.75. And vernier reading. Okay, I can see the fifth one itself coinciding. In fact, the 5, 6, 7 are coinciding, so I just took 5. I don't know, very repeated reading. Like, let me see. Let me go to the next one. All right. Okay. So almost 4 more readings, and then we are done with it. So 7.75 again. 7.75. And what's coinciding is 3. Let me note down 3. Okay. Let me just put the magnifying glass for you to have a look once again. All right. Yeah. So let me now go ahead to the next ring. 3 more readings. All right. So let's note down. This is now 7.75, a bit below. Let me take it as 7.7. Okay, and let me note down the vernier reading, and it is around 44. 44 is what I got. Next one. Again, let's move to the next ring. All right. So then we got 7.7 again. So since we are on the far off rings which are a little less spaced, not much movement is there now. Okay, so the coinciding reading is 38. So let me note it down, 38. Let's go to the next ring. That's it. So 7.7 again, and this is around 29. And we take the last reading now, last bright ring that we get. All right, so that's again 7.7. Yes, 7.7. And vernier reading is the vernier reading is around 12, 13. Fine, so we have taken the readings, and fortunately not much distortions happened while as we were moving, only once or twice at the start, but otherwise it was very smooth, and we got our readings now. So we will now do the calculations and check whether we got our desired result or no. Okay, so see you for the calculations. Okay, so we got our data. Okay, and you might have seen how much difficult it was using a camera to find the Newton's ring. Okay, not so comfortable, not so easy also. All right, but anyways, we have managed, and these were the readings. 0.001 is the least count of the traveling microscope. These were the vernier readings, where we have vernier readings, and this is the main scale reading. You all are second year BSc students. By now you should know how to calculate this. Okay, so this is the final reading that we get from every ring that we have done, from every alternate ring, and so on. So just subtract them and you get the diameter. Okay, just subtract them. Just subtract like from left hand side and right hand side. If I subtract the 15th ring readings, so obviously what I'll get is the diameter. Okay, obviously what I'll get is the diameter of the 15th ring. If I subtract the 14th ring with 14th ring, obviously what I'll get is the diameter of the 14th ring, and so on. All right, so what I expect is that the diameter decreases as I go down. Correct, the 15th ring should be the highest, and 6th ring should be the smallest. But if I see there is somewhere in between, there is one glitch here. So this is something which is little not so correct. Okay, you can see I'm going down. It is very much correct. 445, then 0.387, 465, 5750, all good. 29 and 281, 268, all good, just except this point, which maybe I did some mistake in the vernier, the coinciding reading. Okay, because they are very sensitive, very not spaced so well, so you have to be very careful. So I think I've done some mistake here. So one point is wrong, but rest all are following very well, so should not affect much. And then the square of this, so just take this value, square it up, and you get these values. Okay, then what was the formula? Formula was that radius of curvature was equal to dn square upon 4n lambda, correct? Where lambda was 5890 into 10 raised to minus 8 centimeter, and dn values are here, dn square values. So n is the ring number, 15, 14, 13, so on. So if I do that, I find the radius of curvature to be somewhere between 55 and 50, except this guy whose point I got little wrong. So obviously showing a very higher radius of curvature, and the mean of it is 52.22. okay, next what we go do is plot a graph. I expect that you also plot a graph on your graph paper, graph book. The slope that you will get will be very likely different than what I got. Try it. Okay, but try it and let me know. So obviously write all this scale and all that. You can choose your own scale, need not follow this itself, but I think on the x-axis very likely you will have the same one, but on the y-axis is up to you how you want to change the scale. The slope I get is 0.03, and if I put it in the formula, which is slope upon 4 pi, because d square upon n, so that becomes slope 4 upon 4 pi, I get 55.18. okay, 55.18 is what I get, whereas in calculation I got 52.22, and here I get 55.18, which is quite good. Both the graph and the theoretical readings are agreeing with each other. So we can conclude that our radius of curvature of the lens that is given to us is something around 52 to 55. Okay, so we can write the radius, I mean the result at the end, that the radius of curvature of the plano-convex surface, or the convex surface of the given lens. Plano-convex is a lens, and the curvature of the convex surface is given by this experimental value is 5.22, and graphical method I get 55.18, which is quite good, not bad. Okay, all right. So, and with this we can finish the experiment. Okay, so we have got the radius of curvature using Newton's ring. Okay, so so I hope you enjoyed this experiment, and maybe see you for some other experiment next time. All right, so till then, thank you.